Hi, I'm Zor. Welcome to Unizor. We are talking about solid geometry, and this is part of the introduction into solid geometry, the lectures which are basically explaining what kind of solid objects we are dealing with in solid geometry. This course is presented on unizor.com website, and that's where I suggest you to watch this lecture. Because it has notes on the side, and notes basically are your textbook if you wish. So today we are talking about spheres, and I'm not going to prove any theorems or discuss any important properties of spheres. It's just an introduction what basically is a sphere and what kind of elements of spheres we will be dealing with. Okay, so first of all, the definition of the sphere. Let's consider we have a point somewhere in three-dimensional space, and now I also considering we have certain segment which I call the radius, and this point will be called the center of the sphere. Now I'm considering all the points in the three-dimensional space which are located on the distance of this radius from the center. So it's something like this. Okay, let's assume that I draw a sphere. Now that's really ugly. Let me just put it a little bit more presentable. Okay, this is a sphere, and this is how we will probably draw it. Okay, that's better, right? So the distance from this point to any point on the surface, to this point, to this point, to this point, to this point, all these are equal to radius. Is it a good definition? Well, right now it's definitely not a good definition. Well, first of all, I did not explain what is a distance in three-dimensional space. Now, secondly, I really have to talk about existence of these points which are on this particular distance from any given point. Oh, maybe there are no such points, so we don't have any spheres at all. Maybe there are certain values of radius for which there are no points in that distance from the center. Is it possible? Well, I mean, we have to address this issue. I mean, there are lots of very, very fundamental issues about this. And it's all related to certain axioms which we are establishing or accepting for our three-dimensional space. But let's not talk about these very, very involved and complex issues right now. We will just assume that your intuitive understanding of the sphere as the set of all the points in the three-dimensional space equidistant from the given point O, with a distance given as a radius, that it exists, and that's how basically it looks. So let's consider we have not properly defined a sphere in a strictly mathematical, rigorous way, but we have certain explanation, like Euclid, for instance, did when he explained all these issues. Okay, so that's number one. As far as examples of spheres, obviously you all know that balls basically are spherical, and sphere is actually a surface, not the inside of any solid in this particular case. The surface of our planet is, well, a good approximation of a sphere. So we might actually use some geographical terminology to demonstrate the elements of the spheres. All right, so next we will talk about certain elements. All right, let's assume that you have certain line, a straight line, which is passing through a center of the sphere. How should I better draw it? Well, something from this point to this point, let's say. So this is one edge, and this is another edge. This one is on the front part of the sphere, and the B point is on the back part of the sphere. Another example is just an axis which is here. So any line which goes through a center, let's consider any straight line which goes through a center. Now, this line intersects the sphere at two opposite points. Now, this segment between these two opposite points is called a diameter. So diameter is a segment which has its edges on the surface of the sphere, and it's passing through a center of a sphere. So that's a diameter. Well, example of a diameter as far as our planet is concerned, well, the axis of rotation from North Pole to South Pole, well, that's why I put N and S, by the way, in this particular case. So this is an example of a diameter. Another diameter, for instance, is if one point of equator on Earth is connected through a straight line with an opposite point of an equator on a completely different hemisphere. Okay, so that's a diameter. We have defined it. Now, if you take any other segment which connects two points, this and this, for instance, points, it's inside the sphere from point C to point D. Well, we also have a terminology for this. It's a chord, basically. In some way, it's an equivalent. If you have a flat circle, you have a chord which connects 2 points on a circle. In this case, it's 2 points connected by a segment in a three-dimensional space, where edges of the segment are on the surface of a sphere. Well, obviously, diameter is also a chord, according to this definition. And by the way, it's the longest chord, which needs to be proven, of course. But again, intuitively, as of right now, before I'm going through all these proofs, intuitively you understand that the diameter is longer than any other segment connecting 2 points not going through a center of a sphere. So that's the chord. What's next? Okay, next we are intersecting a sphere with a plane. So let's consider we have a plane. And the plane intersects a circle and this is a plane. So this horizontal plane intersects a sphere, and it basically cuts it in some way. Now, again, intuitively you understand that this is basically a circle, and it is, and it needs to be proven, of course. But in any case, we should basically accept it as of right now without the proof. I will prove it later on. And one of the circles is bigger than the other. If you understand this, the whole this picture, if the plane goes a little bit lower, then the circle will be a little bigger, right? And the biggest one, if the plane would contain the center of a sphere. So in the last case, this particular circle would be called a great circle, because, well, obviously it's bigger than others. So any plane which is passing through a center of a sphere intersects with a sphere along a great circle. Every other plane which does not pass through a center just makes a circle as an intersection between the surface of a sphere and the plane. Okay, now what's the examples of such great circles on the planet Earth? Well, remember we have meridians. Now all the meridians are basically intersection, if you wish, of a vertical, as I'm looking at this of this picture, the vertical plane with a sphere. So it's either this or this or this or this, depending on how this plane is positioned, but it's always passing through a diameter which connects north and south poles. So any plane which is passing through this north-south pole line, the axis of the rotation of the Earth, any plane would intersect with the sphere along some meridian. So any meridian would actually represent a great circle. All right. Now, if you have 2 points on a sphere, so let's take away this plane and take away the insides, and I'm talking about 2 points on a sphere. Let's say this point and this point, A and B. I would like to go from A to B along the surface of a screen, of a sphere. Now, obviously there are many different ways to do it. Here's what I suggest. Let's take the center, O. Now, 3 points, A, B, and O, always define a plane. So let's build a plane which passes through all these 3 points. Now, since it's passing through the O, it's passing through a center, the intersection between this plane and the sphere is some kind of a great circle. Something like this. So, from A to B, it's called an arc. So, arc is a piece of a great circle which connects the ends of these 2 given points, the ends of this arc, and it's part of a great circle, which means it's an intersection of a plane passing through A, B, and O, intersection with the sphere. Now, what's an interesting point is that if you're only going along the surface of a sphere, the arc, which is a piece of a great circle, is shorter than any other way from A to B, or from B to A. So the arc, the part of a great circle, is the shortest distance between 2 points on a surface if you are actually going only along the surface of a sphere. You don't go inside. I mean, obviously the straight segment from A to B, which is inside the sphere, would be shorter, but we can't really do that. I'm talking about only traveling along the surface. Where is it used? Well, actually, most of the routes of airplanes between 2 points on Earth are, well, there are some exceptions, but generally they're trying to stick to arcs of the great circles between 2 points. For instance, from New York to Shanghai, the shortest way, the way how the planes are flying, is actually somewhere over the North Pole. Not as if you look at the map, it looks like it's you can just put a different line from New York to Shanghai, which goes across Europe or Africa or Asia or something. No, apparently the shortest way is over the North Pole, because that's the great circle. That's the arc of a great circle. Okay, again, that needs to be proven, of course, but it's just an interesting observation. So great circles is not something which we just imagine. It's a very real thing and used very much. All right, so that's the great circle. And by the way, this is a good measure of a distance between A and B if you measure within the surface of a sphere. It's a spherical geometry, if you wish, but we'll talk about this later on. Okay, what else is interesting? Okay, now if you have let's return back to the plane which cuts the sphere. Okay, the plane which cuts the sphere it cuts it along some kind of a circle, and this is the plane. Now again, it's more terminology than anything else. It cuts it in basically in two halves. Well, not halves, but two parts. They might be different. If it goes through a center, it's two equal parts. If it's not, then it's just two unequal parts. Now each one of them is called a spherical cap. This part. This part is one spherical cap, and this is another spherical cap. Sometimes they call it spherical domes. So spherical cap or spherical dome. Well, obviously this circle is called a base circle. The plane which cuts it is called base plane. The radius of this circle, which is smaller than the radius of the sphere, is called the radius of a spherical cap. And if you will draw a perpendicular to this base plane from the center of a sphere and up to the intersection with the surface of a sphere, this segment is called an altitude or a height of the spherical cap or spherical dome. Well, and again, you can consider the bottom part as well. It also has a base circle, base plane, and the altitude will be from this point to this. Okay, so what else? One more. The last concept, the last object which we will be considering, the last element, is the following. Let's consider you have a figure which contains a spherical cap, and if you connect each point of this spherical cap, of this base circle, if you connect with the center, so from this base circle to center of a sphere you have a cone, right? So this the circle, the base circle of a cap is considered to be a directrix. The center of a sphere is considered to be an apex, and if we will use this directrix and this apex to construct a cone, then the piece of this cone from the base plane to the center of a sphere is a cone, or piece of a cone if you wish, and together with the cap it's this figure which contains the conical part on the bottom and the spherical part on the top. It's called a spherical sector. Well, again, if you have a plane geometry, what is the sector? Sector is this one, right? Which contains basically a triangle and this piece, right? So it's very, very analogous in a three-dimensional world to the plane. So this is a circular sector and this is a spherical. This is a spherical circle. And obviously we can measure certain things. Again, it has the height of a cap, the height of a cylinder, the height of a conus, of the cone is the difference between the radius of a sphere and the altitude of the cap. So we do know about this cone actually everything, because we know the circle, which is its base, and we know its altitude. So we do know everything about this figure if we know this particular circle. Alright, so these are elements of the sphere which I just wanted to introduce you to. I do suggest you to read the notes, because it's basically more or less the same thing. So just one more time you go through all these terminological issues. And again, the reason of my talking about this is just to introduce you to certain elements which we'll be dealing with in theorems and the problems. So it's just a language which I would like to use in the future to explain certain material. That's it for today. Thank you very much and good luck.